In this lecture, we're going to be looking at air resistance, kinetic energy, and work. So the textbook references in the Halliday, Resnick and Walker textbook for this lecture are section 6.2, 7.1, 7.2 and 3.3. So first of all, a recap of the most important ideas from the last lecture. In the last lecture, we looked in more detail at friction. We saw that friction always opposes motion. So the maximum amount of static friction can be described with the equation that the maximum friction is given by μs, which is the coefficient of static friction, times the normal force. So this isn't always the amount of static friction that acts. This is the maximum possible amount of static friction. The amount of kinetic friction can be modeled as the friction is equal to the coefficient of kinetic friction times the normal force. And we saw that when wheels roll, we use static friction because the contact between the road and the wheel is stationary. But when wheels lock in place, then we've got two surfaces moving across each other and we need to use kinetic friction. The coefficient for kinetic friction is always smaller than the coefficient for static friction. Okay, so air resistance. We've actually seen the effects of air resistance before when we dropped objects in air and in a vacuum, and we saw that the patty case took a lot longer to fall in air than in a vacuum. So what types of things do you expect air resistance to depend upon? So this was a question posed in class. And some things that air resistance you'd expect to depend upon would be surface area, probably also the density of the air. If you think of an object falling through water, which is much more dense than air, it tends to take longer to fall through the more dense medium. You possibly think that it depends on the velocity. So it turns out that the air resistance can actually be modeled by this equation here, where in this equation the C is the drag coefficient. So this depends on the material. Rho is the density of the air or fluid through which the object's flowing. A is the cross-sectional area of the object, and V is the speed. So it depends on the speed squared. So this is the drag force, so it's a force. Okay, so terminal velocity. Can you come up with an expression for the maximum speed an object can fall at? Now I've got a picture of a cat here because there's a somewhat famous study from New York where they investigated the safest levels in apartment blocks for cats to live in. Turns out that the worst floors are around about floors 6 and 7. Above this, the cats have reached their terminal velocity if they fall out of an apartment block, so they have longer in the air to get themselves turned around and relax a little and land on their feet. From below that, below the 6th and 7th floor, they're not in the air as long, so they haven't quite reached their terminal speed, so they hit the ground going at a lower speed. So they just collected this data from accidents around the city. They didn't go throwing cats out of windows. Okay, so if we want to work out the terminal speed of a cat like this, we need to draw a free body diagram. So we've got the weight force, which is pulling it down, and we've got the drag force, which is pulling it up. Now, it's going to stop accelerating when these two things are equal to each other. So it'll stop accelerating, no acceleration, when the drag force is equal to the weight force, because then the net force acting on it is going to be 0. And so we can write, well, a half rho CAV squared is equal to mg. And then we can rearrange this to get our terminal velocity. So V is equal to mg, and then we've got a half here, so that's a 2, divided by C rho A, and we can take the square root of this to get rid of this squared. So this is an expression for the terminal velocity of an object. Now you'll see in physics there's two different approaches that are commonly used. the one that we've been using the most so far is to look at forces. So we can look at forces, which are vectors, and from the forces we can use Newton's second law to get the acceleration of the object, and then from the acceleration we can describe the motion. But another approach is to consider the energy of a system. So energy is useful as it's always conserved within a closed system. We can transfer energy from one object to another and also transform it from one type to another. And energy is a scalar quantity. So formally, the energy of a body is related to its ability to do work. So because it's a scalar, it can be a little bit simpler to use than a vector which has components in every direction. This has just got the one component. So both these approaches should give the same answer, but in some cases, one approach is going to be easier than another. Okay, so we're going to start looking at energy now. So kinetic energy, which we usually give the symbol K, is related to the state of motion of a body. So the kinetic energy is just given by a half mv squared, and energy is measured in joules, which has the symbol capital J. So here's a fairly simple example. We're asked to calculate the kinetic energy of a 1,800 kilogram car traveling at 60 kilometers per hour. So the formula is K is equal to half mv squared. We've got the mass here, and the speed is equal to 60 kilometers per hour, which is equal to 60 over 3.6, which is 16.67 meters per second. So substituting these in, we've got a half times 1,800 times 16.67 squared, and solving this on the calculator, we get 2.5 times 10 to the 5 joules as the kinetic energy of this car. So very shortly we're going to require dot products. Now hopefully these are familiar to you from maths, but just a recap in case you're a little bit rusty or you haven't happened to have come across these yet. If we have a vector A, which is given by A is equal to AXI plus AYJ plus AZK, and another vector B, which is given by B is equal to BXI plus BYJ plus BZK, then if we want to take the dot product between A and B, it is a scalar which is equal to AXBX plus AYBY plus AZBZ. Now geometrically, if we have a vector A and a vector B and we want to take their cross product, it's equal to AB times cos theta, where theta is the angle between them. So if the vectors are parallel, then the angle between them is 0 and cos of 0 is 1. So then we have the maximum cross product. If the vectors are right angles to each other, then the dot product between them is 0 as cos of 90 is 0. So now we know about dot products, we can really look at work. So work is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. So that means if the object's gaining energy, we say that positive work is done on it. If the object is losing energy, then we say the object is doing work, or negative work is being done on it. So work is given by this equation here. Work, which is a scalar because it's energy, is equal to force times distance times cos theta, and this is because it's the dot product between the force which is applied and the displacement of the object. So let's consider the situation below just to show how this makes sense. So we're going to assume that F isn't so large that the block's being lifted up off the surface. We'll assume that vertically there is no net force. So assume the sum of the forces is equal to 0. So because we've got the normal force and the weight force and a component of this force, as long as this force isn't too large, then this will be true. Okay, now we say that work is the energy transferred to or from an object. So work should then be equal to the change in energy And if the object's not moving up or down, then the only type of energy that it's going to have that's going to change is going to be the kinetic energy. So this will be equal to the change in kinetic energy, which will be the final kinetic energy minus the initial kinetic energy, which will be a half mv squared minus a half mu squared, where u is the initial velocity. So we can write this as a half m v squared minus u squared. Now we have the kinematic equation, v squared equals u squared plus 2as, which tells us that v squared minus u squared is equal to 2as, and we can substitute this in here. So we've got that the work is equal to a half m times 2as. So this half will cancel this 2, and we can write this as ma times s. And now s is the displacement in the x direction. So let's put a little x down there to show that that's in the x direction. And a is also in the x direction, as in our kinematic equations, all of these things were in the same direction. So we can say that's in the x direction, which tells us that max, that's the net force in the x direction, times sx. And now in the case when there's no friction or anything, then the only force acting in the horizontal direction is the F force, the Fx. So the x component of the force here is F cos theta, and that's times the distance it goes. So we've shown that this equation here applies at least to this case, if the change in energy is or just a change in kinetic energy, which makes sense. So another question, in which situation is the greatest amount of work done on the block? First of all, a block is pushed against a wall with a force of 100 newtons. Secondly, a block is pushed along a frictionless surface with a force of 10 newtons for 10 seconds. It starts from rest. And third situation, a block is pushed at a constant speed of 1 meter per second along a rough surface by a force with a magnitude of 10 newtons for 10 seconds. Okay, so the correct answer to this one is actually the second one. A block is pushed along a frictionless surface with a force of 10 newtons for 10 seconds when it starts from rest. Now, we can see why that is if we go ahead and calculate the works. So the second part of this was if the mass is equal to 2 kilograms, calculate the work done in each of these cases. Okay, so with this first case, we can just use, well, work is equal to the force times the displacement. In this case, the displacement here is 0, so the total work done is 0. In the second case, we've got the work is done by a force this way, and the force is equal to 10 newtons, and it's acting for 10 seconds. So we can use our force dotted with displacement equation, but we're first of all going to need to calculate our displacement. So we've got, well, the force is equal to 10 newtons, which is equal to the mass times the acceleration, which tells us that the acceleration is equal to 10 newtons divided by the mass, which is 2 kilograms. So that tells us that we've got an acceleration of 5 meters per second. Now we want to know how far it goes, and it's going for 10 seconds and starting from rest. So we can use S is equal to UT plus a half AT squared, where U is 0 because it starts from rest. So this is equal to a half times 5 times it's going for 10 seconds. So this is 2.5 times 10 squared, which is 250 meters. So we can now calculate the work, which is equal to the force dotted with the displacement. The force is the 10 newtons and the displacement is the 250 meters. So this gives us 2,500 newtons as the work done by the force on this object. Now in the next one, a block is pushed at a constant speed of 1 meter per second along a rough surface by a force with a magnitude of 10 newtons for 10 seconds. Now, in this case, because it's not speeding up, Newton's first law tells us that there must be two equal and opposite forces. So we've got the force F pushing it, but this is a rough surface. So now we do have a friction force which is equal and opposite. So the total work is going to be F dot S, the displacement, which we haven't calculated, and we've also got plus the frictional force dot S, but these two forces are equal and opposite. So this is equal to F dot S minus F dot S, substituting in that the frictional force is equal to minus F. And so you can see this is going to be equal to 0. So this one's 0 as well. So this brings us to the work-kinetic energy theorem, which is very powerful and tells us that for particle-like objects, a change in the kinetic energy, which is the final kinetic energy minus the initial kinetic energy, is equal to the work done on the object. So here W is the net work done on the object. So to practice using this, for 1121 students, question 7 in set 2, and for 1131 students, question 9. But now we're going to see an example. Okay, so in this fairly simple example, a particle moves along the x-axis, and we're asked, does the particle's kinetic energy increase, decrease, or stay the same if the particle's velocity changes from minus 3 meters per second to minus 2 meters per second? Well, the change in kinetic energy is equal to the final minus the initial, which is equal to a half m. I'm going to pull the half m out the front because the mass isn't changing. So now I'm going to have the final velocity squared minus the initial velocity squared. So in this case, I've got a half m. Now the final velocity is 2, so this is minus 2 squared minus the initial velocity, which was minus 3 squared. And so you can see this is going to be a negative. So I'll have minus a half m times 4 minus 9, which is times 5. And so the kinetic energy has decreased. So decreased. And for this second one, part 2, I've got that the change in kinetic energy is equal to a half m. And now I've got the final speed, which is 2 squared, minus the initial speed, which is minus 2 squared. And so this is equal to 0. So it stays the same. So then it asks me, in each of these cases, is the work done on the particle positive, negative, or 0? So in part 1, I've got that my kinetic energy decreased, which means that negative work is done on the object as it is losing kinetic energy. And part 2, in this case, my kinetic energy didn't change, so the net work is 0. So the net work is 0 as kinetic energy does not change. So that's how we answer that problem. Okay, so in this question, we have a car traveling at 60 kilometers per hour. So the initial speed is equal to 60 kilometers per hour, which is equal to 60 divided by 3.6, which is equal to 16.67 meters per second. Now it slams on its brakes. It skids in a straight line to a stop. So because it's coming to a stop, we know that the final speed is 0, leaving a 24-meter long skid mark, which suggests that the distance it's taken to stop, the displacement, since it slammed on its brakes, is 24 meters. And we're asked, what is the coefficient of kinetic friction? So we want mu k between the tires and the road. Now, we know that the change in kinetic energy is equal to the work done. Now, on this case, with our car, which is moving forwards, that's the initial velocity, it's got friction acting on it to pull it back. And the frictional force is the kinetic friction because it's skidding, so the tires aren't rolling. So that's given by mu k n. And the normal force in this case is just going to be equal to mg. So we know that the work done is equal to the frictional force times the displacement. Now in this case, the displacement is, say, is in the direction the car's traveling, which is, say, the positive direction, and the frictional force is opposing it. It's in the opposite direction. So we're going to get a negative answer here because these two are in opposite directions. So this is going to be given by minus mu k mg times the displacement. Now the change in the kinetic energy, that's going to be the final kinetic energy minus the initial kinetic energy, which is equal to a half v squared minus a half u squared, and v we've said is 0, the final velocity is 0. So this is equal to a half u squared. So because the work is the same as the change in kinetic energy, we can set these things equal to each other. So minus mu k mgs is equal to minus a half mu squared. So the negatives cancel out, the m's cancel out. What we're trying to work out is mu k. So we've got mu k is equal to u squared over 2, and then we're also dividing by gs. So now we've got an expression that we can evaluate. I generally find it's easier to come to an algebraic expression and then substitute in the last step. So let's substitute in now. We've got 16.67 squared, and that's in meters per second. Then we've got 2 times g, which is 9.8 meters per second, times the displacement, which is the 24 meters. So solving this on the calculator, we end up with 0.59 being our coefficient of kinetic friction. And there are no units given here because the coefficient of kinetic friction has no units. So in this question, we have a force described by 2I plus 1J acts on a 2 kilogram particle-like body initially at rest. So we've got U is equal to 0. Now in part 1, it says write an expression to describe the displacement of the body. Okay, so this is actually slightly challenging because we're going to have to get the acceleration and then integrate it a couple of times to get the displacement. So we know that F is equal to ma. So this tells us that A is equal to F over m, which is equal to, because the mass is 2 kilograms, so we've got 1I plus 1 divided by 2, so 0.50 j. So this is for the acceleration, and the acceleration is equal to dv dt. So we can integrate this and say, well, the integral of 1.0i plus 0.50 j dt, going from time is 0 to time t, is equal to the integral of dv from u, which we're told it's initially at rest. So this is 0 up to speed v, and so we can write, well, 1.0 ti plus 0.50 tj is equal to v, which we know is equal to the displacement dt, so the derivative of the displacement. So now we're going to integrate this again. So now we're going from 0 to t, and we've got 1.0 ti plus 0.50 tj dt, which is equal to the derivative of the displacement. And if we're measuring the displacement from its initial position, then it starts at 0 and it's going up to some displacement, which we will call s. So integrating this, we get 0.50 t squared I plus half of half is 0.25 t squared. And then when we substitute in 0, we've got zeros here, so that's right, substituting in these limits. And then when we integrate this, we have s. So write an expression to describe the displacement of the body. This is our expression to describe the displacement of the body. But I left off my j, so I need to put that j back there. It was there, it's there. So this is a vector expression. Okay, part 2, so that's part 1. Part 2 now asked to write an expression for the work done by the force in a time interval t. So we now know the displacement at time interval t, and we've got an expression for the force. So we know that the work is equal to the dot product of the force with the displacement. So this is 2i plus 1j times 0.50 t squared I plus 0.25 t squared j. So taking the dot product of this, we multiply the I components together, and so this is 2 times 0.50 t squared, and then we also multiply together the j components, so that's 1 times 0.25 t squared, and so this gives us 1 t squared plus 0.25 t squared, which gives us 1.25 t squared as the total work done in a time interval t. And then part 3 tells us to use this to determine the speed of the body at time t. So now we can use that the work is equal to the change in kinetic energy of the object, which is equal to a half mv squared minus u squared, brackets around there because the half m applies to both of them, but u was equal to 0, so this is equal to a half mv squared. So we've got, well, a half times m, which is 2, times v squared is equal to the work, which is 1.25 t squared, and these cancel, and I end up with v squared is equal to 1.25 t squared, so v is equal to the square root of 1.25 times t, which I can write as 1.1 t if I want. Now it's worth just checking our answer, because back in this step here we did get an expression for the velocity at time t, so we have that the velocity is equal to 1.0 t plus 0.50 t. So if we draw a little diagram, we've got 1.0 t and then we've got 0.50 t. So the speed is going to be the resultant here. So that's the square root of 1 squared plus 0.5 squared times t, which is also equal to 1.1 t. So these are in fact the same expression. So that suggests that we've done it correctly. So in this problem, we've got a 5 kilogram block which is pushed up a long inclined plane inclined at an angle of 30 degrees. So let's start by drawing our diagram. 30 degrees, here's our 5 kilogram block, so m is equal to 5 kilograms, and it's pushed up this way. The coefficient of kinetic friction between the block and the plane is 0.4, so mu k is equal to 0.40, while the coefficient of static friction, mu s, is equal to 0.60. The block is originally travelling up the slope with a speed of 10 meters per second, so u is equal to 10 meters per second up the slope. And in part 1 we're asked what is the initial kinetic energy of the block. Okay, so that's not too hard. The kinetic energy is equal to a half mu squared, so this is equal to a half m is 5, u is 10, and so solving this we end up with 250 joules as the initial kinetic energy. So how much work is done on the block as it moves up the slope? Okay, well, it's going to move up the slope until it comes to rest. So the final kinetic energy is going to be 0 because the block is at rest. So this implies that the change in kinetic energy, which is the final minus the initial, and we calculated the initial here, is going to be minus 250 joules because it's 0 minus 250. And that's going to be equal to the work done on the block. So we're going to have minus 250 joules of work done on the block. Part 3, how far up the slope does the block move? Okay, so we know that the work done is equal to minus 250 joules, and we also know that that is equal to F dot x. Now to work this out, we need to know the total force which is acting, as this is the total force parallel to the slope if x is the distance up the slope. So let's draw all the forces which are acting on our block. We've got the weight force mg, which is pulling it down, which we can, as always, divide into our components. Here we've got mg sine theta, and here we've got our mg cos theta. Now we also have the normal force, which is perpendicular to the slope, so it's acting up like this. And because the net perpendicular force is 0 and the only two perpendicular forces are the weight force and the normal force, we've got that this is equal to mg cos theta. And then we also have a frictional force. Now the frictional force opposes the motion. So the motion is going up the slope. So we've got the frictional force down the slope. And the frictional force is equal to mu k times the normal force. And we've got the normal force up here. So we can say, well, this is going to be equal to the force, which is equal to minus mg sine theta. So that's the component of the weight force. And then we've also got the frictional force, which is minus mu k times n, where n is mg cos theta. And the minus sign here is because it's down the slope, times x. So we can solve this to find x, which is the distance it travels up the slope. So this is equal to 250 divided by, now mg, that's a common factor in each of these. So I'm going to pull that out the front, and my m is 5 times 9.8. And then I've got my sine 30 plus my mu k, which is 0.40 times cos 30. And solving this on the calculator, I get 6.03 meters, which I should just give to two significant figures. So 6.0 meters up the slope. Now we can just check this with the displacement that we calculated at the end of the friction lecture, and it turns out that we do get the same answer. So we've now got the same answer with the energy approach as we got when we were purely considering the forces. So have a think about which approach you found easier. There's not necessarily one which is easier for everybody for all questions, but you do need to be familiar with both of these approaches.